second talk on survey of finiteness properties of local cohomology modules. So Kamran, you are welcome to start your seminar.
Thank you. Welcome to the second session of my talk. As you see, the sections of my talks is the following, and we stop in this place at the derived category approach. Just for people who are not who were not in the previous session, I recall some setting and start with saying some notations. R denotes a commutative Noetherian ring with identity, and by M of R, we mean the category of R modules and R homomorphisms. Always A will denote an ideal of R, and M an R module. The A torsion functor from the category of R modules to itself is defined by the following. For modules, is gamma I of M is the set of all elements in M that annihilated by some power of A. And for homomorphisms, gamma A of F is just restriction of F to gamma of AM. And for each non-negative integer I, the highest local cohomology module functor is the i's right functor of gamma A. And another things that one should recall here is the definition of cofiniteness. An R module L is said to be a-cofinite if its support is contained in V of A, and all X modules, all of these X modules are finitely generated. And I recall the main finiteness problems in local cohomology. Let N be a finitely generated. People searching about the cases that these local cohomologies are Artinian, when they are finitely generated, and when are the stroke of these local cohomology modules are finitely generated. And also people ask about the associated problem ideals of these modules, and also people looking for the cases in which local cohomology modules are a-cofinite. And finally, people look about the cases that the Boss number of these modules are finite. So now we continue our discussion. In this part, we want to introduce a generalization of local cohomology that contains all previously known generalization of local cohomology. For that, I start with recalling the definition of abelian category. An additive category C is said to be abelian if every morphism in C has a kernel and a co-kernel. And every monic in C is the kernel of its co-kernel, and every epic in C is the co-kernel of its kernel. The notion of that category was part of PhD thesis of Vardier in 1960 under supervision of Gorodedic. For any abelian category C, they introduced its derived category. And here we are not going to define it technically, just be focusing on the derived category of the category of R modules. And in this situation, the things are much easier. So let D of R denote the derived category of M of R. M of R is the abelian category of R modules and R homomorphisms, as I said before. So from the definition of that category, it follows that the objects in D of R are complexes of R modules. So the objects are known. And also, we should notice that quasi-isomorphisms between complexes in this category are isomorphisms. So any two complexes that are quasi-isomorphic in this category, they are isomorphic. And just for people who are not so familiar with the notion of quasi-isomorphism, quasi-isomorphisms between quasi-isomorphism between two complexes x and y is morphisms of complexes that in homology induces isomorphisms. And here we have to introduce some more notations. By this notation, we mean all complexes that homologically bounded to the left. And by this, complexes homologically bounded to the right. This means that homologies of all complexes X with this property that all homologies of X are 0 for I large enough. And this is the full subcategory of all complexes like X, such that hi of X is 0 for all I small enough. And by this notion, we mean the intersection of these two full subcategories. So this will denote the full subcategory of homologically bounded complexes. And by this notion, we mean the full subcategory of complexes with finitely generated homologies. So next, we are going to define projective resolutions and injective resolutions in the category of D of R. An R complex P of projective modules is said to be semi-projective if the functor hom R of P and blank from D of R to D of R preserves quasi-isomorphisms. By a semi-projective resolution of an R complex X, we mean a equation like this when P is semi-projective. Dually, we can define semi-injective complexes and semi-injective resolutions. A complex consisting of injective modules is called semi-injective if this functor preserves quasi-isomorphisms. And by a semi-injective resolution of an R complex X, we mean a quasi-isomorphism like this, in which I is semi-injective. Having the notion of semi-injective resolution and semi-projective resolution, we can define the notion of R hom and tensor L, which makes things very easier in the right category. It is known that any complexes possesses a semi-projective resolution and also possesses a semi-injective resolutions. Let X and Y be two R complexes. The notion R hom X and Y can be computed as following. We just care about its computation and not about its exact definition. It can computed like this. R hom X and Y, you can in the same quasi-isomorphic class of hom of P and Y, where P is a projective resolution of X, or it's the same as hom of X and I, where I is an injective resolution of Y. When we define this notion, we can define the X modules of two complexes for any integer, for any integer I. The ith X module of X and Y is defined as the minus I homology module of this complex. And also we can define the notion of tensor L for two complexes X and Y. This complex can be computed in this way. It's the same as P tensor by Y or X tensor by Q, where P is an injective, P is a projective resolution of X, or Q is a projective resolution of Y. We can compute it in two ways. When we have this, we can define Tor modules for each integer I. The ith Tor module of X and Y is defined as ith homology module of this complex. The next definition, let Z be a subset of a spectrum of R. We call it a stable under specialization subset if B of P is contained in Z for every P in Z. So whenever P is in Z, all other elements in B of P also are in Z. We have plenty of examples for this notion. Here we record some of them. For any ideal A of R, V of R is a stable under specialization subset of a spec of R. For any two ideals A and B, W of A and B, which we defined in previous session, is stable under specialization subset of a spec of R. Any subset of max of R, the set of maximal ideals of R, is stable under specialization subset of a spec of R. And for any R module N, the support of N is stable under a specialization subset of R, of aspect of R. And the fifth part says that the vice versa is also true, that for any stable under a specialization subset Z of aspect of R, one can see that Z is equal to support of this module. Direct sum of all R over A's, where A runs in F of Z. F of Z is the set of all ideals of R, such that V of R is contained in Z. So by this part, stable under specialization subsets of aspect of R is nothing else of support of modules. And the sixth part, the union of any family of stable under specialization subsets of aspect of R is again stable under specialization subset of aspect of R. And now we are going to define the derived local cohomology. Let Z be a stable under specialization subset of aspect of R. We first define the functor gamma Z from the category of R modules to R modules. Gamma of Z of M is those elements in M with which their supports is contained in Z. And for an R homomorphism F from M to N, gamma Z of M is restriction of F to gamma Z of M. Then the right total right functor R gamma Z of from the category of D of R to itself can be computed by, for any complex X, can be computed by gamma Z of I, where I is any semi-injective resolution for X. So now we have this notion, and we are going to define local cohomology. For each integer I, gamma z I of x is the minus I homology of this complex, R gamma z of x. Here, note that for local cohomology for modules, we only have local cohomology in positive i's and non-negative i's. But here, there might be non-negative local cohomology for negative i's. Now, we are going to show that this local cohomology is the most general notion of local cohomology. It all other previously known generalization are special cases of this. Just for recalling them once more, and then I will tell you about the remark. Local cohomology with two modules defined in this way. This is one of the generalizations of local cohomology. And W of A and B for two ideals A and B is the set of all P in respect of R with this property. And using this, we define this type of local cohomology. And also we present local cohomology with respect to a system of ideals in the previous session. So in this remark shows that this local cohomology is the most general local cohomology that we can have in commutative algebra. The ordinary local cohomology can be seen as follows. Let A be an ideal of R and take Z to be V of A, and let X be the module M. Then the ordinary local cohomology is just this. And for let M be another R module by a result of Yosemite. If M is finitely generated, then this local cohomology is nothing else, this one, Hz of I of X, where for every non-negative I, where Z is V of A and X is R home of M and N. And for local cohomology with respect to two ideals, we can have this. This local cohomology is the same as local cohomology of X with respect to Z, where Z is W of A and B, and X is the module M. And when phi is a system of ideals, then H phi I of M is isomorphic to Hzi of X for a non-negative integer I, where Z is the union of P of A when A runs in phi, and X is in M. And the last one that I didn't define in previous session because the definition of abstract local cohomology functor need a lot of preliminaries. I just here bring a result of Yoshino and Yoshizawa that any abstract local cohomology delta is just local cohomology with respect to a certain stable under specialization subset of Z for any abstract local cohomology like delta. We have a stable under specialization subset Z such that these two functors are naturally equivalent. Here, I bring an example that local cohomology with respect to a system of ideal can be different from the local cohomology with respect to any ideal. Let R be a finite dimensional Gorenstein ring such that this set is infinite. The set of all maximal ideals with the same height as dimension of R. So this is a Gorenstein finite dimensional ring such that this set of maximal ideals is infinite. In the examples, we said that any subset of the set of maximal ideals is a stable under specialization subset of a spec of R. So this is true for this. Now, one can check that the injective, the minimal injective resolution of R has the following form: the direct sum or E injective envelope of R over P's when height of P is 0. Then this is in the first place, in the 0 place. In the first place, we have this, and etc. And now, by a straightforward computation, we can see that the local cohomology of R with respect to Z at the point dimension of R is the last module in the above resolutions. So because Z is infinite, this module is not Artinian. By a classical result, it is known that for any ideal B of a finite dimensional commutative Tehran ring T, the T module HB dimension T of T is Artinian. So because this module is not Artinian, we conclude that it is not isomorphic to local cohomology of R with respect to any ideal at the point dimension of R. So local cohomology with respect to system of ideals can be different from local cohomology to respect a general subset, stable under specialization subset of a spec of R. So as I told you in the previous session, among the finiteness problems, the cofinite is very important because cofinite modules have many good properties of Artinian modules and also finitely generated modules. In the same way, their class is very larger than both of these classes of modules. So here we focus on this notion, and we review some results in this area. In this section, we report my joint research with Hossein Faridian and Masoud Tousi on cofiniteness that appeared in these 3 papers. You can see them at the references list. In 1969, Hartshorne introduced the notion of cofiniteness for modules that I recall it in the beginning of this session. And also he introduced the notion of cofiniteness for complexes. For complexes, his definition is as follows. He defined this notion just in the case R is aadically complete regular ring of finite Coulomb dimensions. So in a very restricted case, R is aadically complete regular ring of finite dimension. By his definition, an R complex X is to be ecofinite if X is isomorphic in direct category, I mean, isomorphic to R home of Y and R gamma A of R, where Y is a complex with finitely generated homologies. After defining cofinite modules and cofinite complexes, he proposed these three questions. These three questions that are very important in the theory of cofiniteness. The first question is the following: is the local cohomology module of a finitely generated module N with respect to A are cofinite for any I? The second question is the category of all ecofinite R modules, which denoted by this notion, is an abelian subcategory of the category of R modules. And the third question, is it true that an R complex X is ecofinite as an R complex if and only if its homology modules are ecofinite as modules? So Hartshorne himself, by this example, shows that the answer to the first two questions is negative in general. Let K be a field, and let R be this ring, A be the ideal generated by U and V, and P be the prime ideal, principal prime ideal generated by this element, and take T be R over P. Then R is the regular domain of dimension 4, and T is a non-regular domain. He showed that this module is not finitely generated. So this local cohomology, the second local cohomology of T with respect to A, is not cofinite, ecofinite. So the answer to the first question is negative. Also, we have this exact sequence. One can see that local cohomology of R, the second local cohomology of R with respect to A, is ecofinite. Here, this local cohomology appeared as a co-kernel, a map between two ecofinite modules, but it is not ecofinite. So by definition of abelian category, this is not an abelian category. The category of ecofinite module is not abelian, because here we have two ecofinite module and an R homomorphism between them, and the co-kernel of these R homomorphism is not ecofinite. After presentation of these three questions, many mathematicians attack to these two questions, and they obtained many results about these two questions. But for this question, almost nobody care about the third question. So Hartshorne himself, considering question 1 and 6.1 and 6.2, obtained the following result. When the answer of these two questions is positive, whenever A is a principal ideal generated by a non-zero divisor and R is a-adically complete regular ring of finite group dimension, or A is a prime ideal with dimension of R over P is 1, and R is a complete local ring. So the answer to these two questions, question 6.1 and 6.2, are true for in a very restricted cases. And many people try to exclude some restriction in original results of Hartshorne. And there are many people who are working in area, people like Honeke and Co., Delfino and Marley, Kawasaki, Melkerson, and many other people. And nowadays, this result has this form, the original result by Hartshorne, generalized by these people and some other people, more people, and now it has the following form. Let A be an ideal such that either arithmetical rank of A is less than or equal to 1, dimension of R over A is less than or equal to 1, or dimension of R is less than or equal to 2. Then for any finitely generated R module N, and for any non-negative integer I's local cohomology of N with respect to A is A cofinite, and the full subcategory of A cofinite modules is denoted by this notation, is an abelian subcategory of the category of R modules. So in any of these three cases, the answer to both questions of Hartshorne are affirmative. In the case arithmetical rank of A is less than or equal to 1 is due to works by Kawasaki. The case dimension of R over A, dimension of R over A is less than or equal to 1 is due to works of Melkerson and also Bahmanpur and Naqipur and Siddiqui, and also another work by Bahmanpur and Naqipur. And the case dimension of R is less than or equal to 2. It's done by Melkerson in two different, in these two theorems. You can see this case. And checking cofiniteness is not easy because you should care about infinity many X to see whether they are finitely generated or not. Here, we are going to establish a finitely many step criterion for seeing whether a module is a cofinite or not. For that purpose, first I should recall the definition of local homology. Local homology is the dual theory for local cohomology. As I recall in the beginning of this session, local cohomology is the right-derived functor of a torsion functor. One can see easily that completion functor is the dual of a torsion functor. So the left-derived functor of completion functor can be considered as dual theory for local cohomology. So for each non-negative integer I, the I's local homology functor defined as the I's left-right functor of the functor completion with respect to A. So here, homological dimension of M is defined as the last point that local homology with, at I with respect to A of M is non-zero. By a result of Greenlees and May, one can see that homological dimension of A and any module M is less than or equal to homological dimension of R with respect to A. So this is always is finite and bounded by this. So always is bounded by the number of generator of A. And now I present the criterion that I said before. Let M be an R module such that its support is contained in V of A. The following are equivalent. The first part, M is a cofinite. Second, Tor I of R over A and M is finitely generated for every I between 0 and homological dimension of M with respect to A. And Tor I of R over A and M is finitely generated for all I's. And so here, the equivalence of the first condition and second one, we have a finitely many step criterion. So it's a make checking cofiniteness much easier. Now, as a result of theorem 6.7, we have the following. If homological dimension of R with respect to A is less than or equal 1, then the full subcategory of A cofinite modules is an abelian category of the category of R modules. Here, because the category of A cofinite modules is a full subcategory of category of R modules, for establishing this theorem, we only need to check whether for an R homomorphism F between two A cofinite modules, whether the kernel of F and the co-kernel of F are equifinite or not, because other properties for abelian category automatically hold for this subcategory. We just need to see if M and N are two cofinite R module and F is an R homomorphism between them. We should check whether the kernel of M and co-kernel of kernel of F and co-kernel of F are a cofinite or not. From this homomorphism, we have this short exact sequence. The long short exact sequence that Tor produces, we have this. So by theorem, since M is a cofinite, this Tor is finitely generated by theorem 6.7. So here, this module also should be finitely generated. By this theorem, it's enough to see if I want to check a module is a cofinite or not. It's enough to check the first and the zero Tor and the first Tor of R A against M are finitely generated, because here homological dimension of A and R with respect to A is less than less or equal to 1, and by the result that I mentioned above, homological dimension of any module with respect to A is less than this integer. So only we have to check to see that the zero Tor of RA and co-kernel and also the first Tor are finitely generated. So here we, from this exact sequence, we deduce that this is finitely generated. Also, we have this short exact sequence, which induces the following long exact sequence. Here, by 6.7, these three modules are finitely generated. So since this module is finitely generated, we deduce that this module is finitely generated. Since these two modules are finitely generated, we deduce that Tor of Ri, first Tor of Ri and co-kernel of F is finitely generated. So using Theorem 6.7 again, we conclude that co-kernel of F is eco-finite. And it's quite easy to check that if in exact sequence, two modules are eco-finite, the third one also should be eco-finite. So here, co-kernel of F is eco-finite. We saw some minutes ago, and is eco-finite by assumption. So the image of F should be eco-finite. Now look at this exact sequence. M is eco-finite, image of F is eco-finite, so kernel of F also should be eco-finite. So for any R homomorphism F between two eco-finite modules, we show that kernel and co-kernel are also eco-finite. This shows that the category of the full subcategory of eco-finite modules is abelian. So in view of Theorem 6.7, the proof for this theorem, Theorem 6.8, was quite easy. But as we mentioned in the previous session, always cohomological dimension of R with respect to A is smaller than or equal arithmetical rank of A. But there are examples to show that this inequality can be strict. An example by Hillas and Stuttgart. Let K be a field and take S to be this ring for more power series over 4 intermediates, and take F be this, G be this, and H be this element, and let R be S over Fs, and A be the extension of the ideal generated by FGH to R. Then R is a Noetherian loop covering of dimension 3. Cohomological dimension of R with respect to A is 1, but the arithmetical rank of A is greater than or equal to 2. So here this can be strict. So Theorem 6.8 is a genuine generalization of first part of this theorem, because there are cases that in which cohomological dimension is less than or equal 1, but arithmetical of A is greater than or equal to 2. I said that the definition of Hartshorne for eco-finite complexes is just for the case R is a finite dimensional regular ring, which is adically complete. So it's a very restricted situation. And now we define ecofinite complexes in a very general case, in a more general case. Let X be a complex. We say that X is ecofinite if its support is contained in V of A. Support of a complex, by definition, is the union of support of its homology modules. So if support of X is contained in V of A and R, the complex of R, home of R, A, and X, has finitely many homology modules. So if we take X to be a module, we recover the previous definition of ecofinite modules, because homology modules of these is nothing else X of R over I, A, and X. In this result, we show that in our definition coincide with the Hartshorne definition whenever we can have the definition of Hartshorne. Assume that R is adically complete and X be a bounded complex, homologically bounded complex. The following are equivalent. X is ecofinite in our definition, I mean. The second, X is isomorphic in that derived category with R gamma A of Z for some Z which is homologically bounded and its homologies are finitely generated. And the third, in derived category, we have this isomorphism. X is isomorphic to R home of Y and R gamma A of T, where Y is a homologically bounded complex with finitely generated homologies, and R has a dualizing complex D. So whenever we have definition cofiniteness by Hartshorne definition, it's equivalent with our definition. But his definition is just for the case the ring is finite dimensional regular ring, which is adically complete. Now we have this theorem. Suppose that I's local cohomology of n with respect to A is ecofinite for every finitely generated R module n and every non-negative integer I. And the subcategory of ecofinite modules is abelian. Then I's local cohomology of X with respect to A is ecofinite for any complex with finitely generated homologies and every integer I. So for proving this, we have to use a technique, a very powerful technique in that category, which is way out technique. Way out technique is a technique that you can use it for extending results that hold for modules for complexes. And as I said before, in the literature, there isn't any attempt to solve the third Hartshorne question. Here is our result for third question. Let X be homologically bounded to the left complex. The following assertions hold. If hi of X is ecofinite for every I in Z, then X is ecofinite. Recall that what was the third question? Just a minute. The third question was this. For a complex X, is it true that X is ecofinite in Hartree sense if and only if all of its homologies are ecofinite as modules? So the first part of our result in this regard, if hi of X is ecofinite, then X is ecofinite by our definition. Assume that R admits a dual existing complex D, A is contained in the Jacobson radical of R, and local cohomology, I's local cohomology of Z with respect to A is ecofinite for every complex Z, which is homologically bounded to the left and has finitely generated homologies, and every I. If X is ecofinite in the sense of Hartree, then all homologies of X are ecofinite as modules. And we immediately can have this result. Assume that cohomological dimension of A and R with respect to A is less than or equal to 1, or dimension of R over A is less than or equal to 1, or dimension of R is less than or equal to 2. And then the following hold. Local cohomology of X with respect to I's local cohomology of X with respect to A is ecofinite for any complex X with finitely generated homologies and every integer I. And the second, assume that R admits a dualistic complex D and A is contained in the Jacobson radical of R. Then, if X is homologically bounded to the left complex and is ecofinite in the sense of Hartree, then all of its homology modules are ecofinite as module. The next result reveals the relation between these three coefficients of Hartree. In the beginning, these coefficients look that they are independent of each other, but this result shows that they are not independent of each other. Consider these three conditions: local cohomology of any finitely generated module with respect to A, all of local cohomology of N with respect to A are ecofinite, and the subcategory of ecofinite modules is abelian. The second, all local cohomology of any complex X with finite homologies with respect to A is ecofinite. Third, an R complex, a homologically bounded complex X is ecofinite if and only if all of its homology modules are ecofinite. Then I implies 2 and 3 implies I. Furthermore, if R is aedically complete, then all of these three conditions are equivalent. So there is a close connection between Hartree coefficients. So as an immediate corollary, if R is aedically complete and either cohomological dimension of R with respect to A is less than or equal 1, or dimension of R over I less than or equal 1, or dimension of R is less than or equal to 2, then an R complex X, a homologically bounded complex X, is ecofinite if and only if all of its homology modules are ecofinite. Now we want to have the most general cofinite result for cofiniteness. So we want to generalize the notion of a cofiniteness to a stable under specialization subset of a spectra of R. For such subset of a spectra of R, we say a complex X is Z cofinite if its support is contained in Z, and R home of RA and X, all of its homology modules are finitely generated for any choose of A in F of Z. I recall that F of Z, is the set of all ideals of R, such that V of A is contained in Z. And the second part of this definition, we denote the full subcategory of Z cofinite modules by this notion. And also we here introduce some notion. The cohomological dimension of X with respect to Z is the supremum of I's, such that, here I should say in Z, not in N, such that I's local cohomology of X with respect to Z is non-zero. And support of X, as I said before, is the union of support of I's homology of X when I runs in Z, and the dimension of X for a complex X is defined as supremum of dimension of HIX minus I when I runs in Z. Now we have the most general cofiniteness results. Let Z be a stable under specialization subset of a spectra of R, such that either R is semi-local and cohomological dimension of R with respect to Z is less than or equal 1, or dimension of Z is less than or equal 1, or dimension of R is less than or equal to 2. Then the subcategory of Z cofinite modules is abelian. And the last result, if Z is as above and X is a left-bounded complex with finitely generated homology modules, if either R is semi-local such that this condition holds, or dimension of Z is less or equal 1, or dimension of support of X is less than 2 or equal to 2, then all local cohomology of X with respect to Z are cofinite. At the end here, I suggest some references for having more information about local cohomology. If one need to self-content textbook, I refer he or she to the interesting book by Bradman and Shaw. If somebody wants to know about the historical view, I refer him to two lecture books by Hartshorne. For a survey, one can refer to two papers by Honecke, one by Liebznig and one by Schenzel. For applications of theory of D modules in local cohomology, one can refer to interesting paper by Liebznig. For draft category approach, one can refer to the lecture note by Hartshorne entitled Residue and Duality, a paper by Lippmann, a paper by Winkel and Shan-Wagstaff, and also our paper, joint paper with Faridian and Tusi. And for cofiniteness, there are plenty of good papers, but among them one can mention to the original paper, which the notion introduced by Hartshorne, a paper by Honecke and Co., a paper by Delfino and Marley, paper by Melkerson, a paper by Kawasaki and Edo, a paper by Yoshida, and a paper by Bahmanpur and Nakipur, and also the paper, our paper that I mentioned above. Thank you for your attention.
Thank you very much, Kamran. We are ready for some questions now from audience. You can open their mic. Yeah, I have some basic question, Kamran.
Go ahead, please.
Yeah. So, important theorem about local cohomology is the local duality theorem.
Yes.
Do we have a version of that in this general theory in derived category?
Yes, sure. In fact, it should be interesting for you that the original draft of this theorem was appeared in the lecture note by Hartshorne, Residue and Duality. And at that reference, it is described in derived form. So it's in derived category, it's much easier to describe local duality.
So one uses the dualizing complex there?
Yes, sure. Yes, yes.
Okay. Yeah. And what about these nice results about finiteness of associated primes in characteristic P? Do we have versions of those?
As I said in previous session, if a local cohomology module is acofinite, then the set of its associated prime is finite. So whenever you have acofiniteness, the finiteness of associated prime is automatic.
Okay. So you mean to say we get new proofs of these old results?
In fact, we have some generalization, not new proofs. In Theorem 6.8, in Theorem 6.8, before this result, the best result was that if arithmetical rank of A is less than or equal to 1, then we have that this subcategory is abelian. But we extended to, instead of saying arithmetical rank is less than or equal to 1, we say homological dimension of R with respect to A. And by this example, it's become clear that we have the cases that our result can be covered by the previous one. Okay. For cofiniteness, for the first two questions, there are many papers. But for the third one, maybe our result is the only one after Hartshorne himself. And also, one of the results that I mentioned reveals a nice relation between these three questions.
Mm-hmm. Okay. Yeah, thank you. Any questions? Okay, I don't see further questions. So Kamran, thank you very much for your two talks, for coming to this seminar. Next week, we have one more talk on local cohomology